I'm going to explain gradient descent in a very easy way so that you can love it as much as I do. Okay, the whole motivation of gradient descent is to explain what we said in the last video. And if you haven't watched that video, please go and do so. But if you haven't, it's completely fine. I think you can understand gradient descent without necessarily having to watch it. So let's start. Let's say I were to give you a function, y is equal to x squared. Okay, and I were to give you this function, you can basically plot this graph very simply and obtain this shape. Okay, this is y, this is x. Simple. Let's replace y with j of theta. I haven't done anything fancy. I'm just renaming y as j of theta, right? Nothing fancy here that I'm doing. Don't complain. And I'm going to rename x to just be theta. So j of theta is equal to theta squared. Some function called j of theta. So you can be comfortable with me removing j of theta and this being theta, right? So I could ask you, what is the minimum value, okay, of j of theta, right? Okay, and you would happily say the minimum value of j of theta is 0. And what is the value of theta at that specific minimum value of j of theta? You can say, well, theta is 0, right? So this is the minimum possible value of j of theta. Now, what if I were to ask you to create a way in which you can find this minimum point, right? A way in which you can find this value over here, starting at another given value. Well, let's assume you were to start here at theta 4, okay? Some value of theta over here. And I would ask you, can you minimize this function? You have to start at a guess, right? You have to start with this specific value. And I would ask you, can you minimize this function up until you reach this point? How can you do that? How can you basically find the value of theta where you have the minimum possible value of j of theta? Turns out this is actually fairly simple. What you can do is find the gradient of this function. Okay, so the gradient of this function is basically going to be dj over d theta. I'm not doing anything fancy. I'm just differentiating this. You're going to get 2 theta. Okay, what this tells you is that for every value of theta that you have, this will give you the gradient at that point. Okay, so if you're at theta 4, you started off with theta 4 and you want to find the minimum value of j of theta, the value where j of theta is the lowest value, you can find the gradient at every value of theta that you start at. So at this point, the gradient is basically something like this. Okay, so sorry, excuse my bad drawing. But this is basically going to be your gradient. Okay, so dj over d theta is going to be equal to 2 theta, which is going to be, let's say theta 4 is equal to 4. No pun intended. Okay, so dj theta is going to be 2 theta, is going to be 8. So if you realize that this gradient is 8, what can you do, right? How can you reach the minimum possible value of theta? What this gradient tells you is very simple. This gradient tells you if you're to increase values of theta, so if you're to increase values of theta and go in this direction, okay, increase values of theta and go in this direction, then this function is going to increase, right? Like that's basically what the gradient tells you, right? If you're to increase values of theta, the j of theta is going to increase, right? Because bear in mind that the gradient is the slope of this line. It tells you what will happen as the theta value changes, right? That's why it's positive. So if you move opposite to that, so if you're to move in this direction, right, you basically arrive at the lowest possible value of theta. Does that make sense? So if you start off with 4, if you're to subtract 8, you're going to arrive at negative 4. Okay, so if you're to subtract your gradient, you're going to get a lower value of theta if you're to just subtract your gradient, right? If you're to add it, you'd get 12, okay, which is far away. 12 is like over here. It's going to have a very high value of j of theta. So if you're to subtract your gradient, wherever you are, if the gradient is positive, if you're to subtract it, you're going to end up with a value of negative 4. Okay, so we're here. Now we're here at negative 4. So this is a game that we're playing. It's called chasing the gradient, right? Gradient descent. We're going to explain what that means. So theta 4, or the value of theta now is equal to -4. Okay, then we go to this point and we try to find the gradient of this value. And then we do this. Okay, the gradient here is going to be -8. Okay, because I'm going to plug in -4 into 2 theta is going to be -8. Then you realize, wait a minute, there's something happening here. Something fishy is happening. If I were to increase values of theta, I'll get more negative, right? This function is going to get more negative, right? The value of j theta is going to increase by increasing values of theta in this negative direction. So what I need to do is basically decrease my values of theta so that I can arrive at the minimum value of theta. So what you can do is basically move in this opposite direction. So you can basically say, well, okay, -4 minus -8. So you can basically subtract that negative gradient again, and you end up with, in this case, you're going to end up with 4. Okay, then you go to the other side, you go back, you go to the other side, you go back. So you keep on oscillating in this manner. Turns out you can avoid this if you add what is known as a step, right? So a step size. Okay, so if you were to say, whatever value of theta that you have, right, subtract a small step, right? Take smaller steps, subtract a small step multiplied by the gradient. If you're to do this, turns out something cool can really happen. And I'm going to show you guys that. So what this means is that, look at the gradient at where you are. So we're at theta is equals to 4. If I were to say my small step is 0.1, for example. So if my theta is 4, if my theta is 4, and I identify that my gradient is 8, it means I must move in this direction, right? I must move in this direction, so I need to subtract my gradient so that I can get a smaller value of theta 4. So if I take a small step, right, of 0.1, and then I input my gradient over here, 0.1 times 8, that's going to be what? 0.8. It's going to be 4 minus 0.8, which is going to be 3.2. And you're going to arrive at a value that is 3.2, which is over here, right? And you can calculate the gradient at that point as well. You calculate the gradient at that point, you plug it in to 2 theta, you get a new value of the gradient, and you say, what is that new value? So we now have 3.2 minus, right? You try to find the value, so this is going to be 0.1. The gradient, when we have 3.2 times 2 is basically going to be 6.4, minus 6.4 is going to be equal to what? Okay, so 3.2 minus 6.4, so let me erase this. 3.2 minus 0.1 times 6.4 is essentially going to be equal to 2.56. We go to 2.56 over here, and you keep on doing that, it's going to converge, right? At some point, it's going to reach this specific value over here, such that the gradient is going to get 0. You see that my gradient is getting smaller, right? If you try to find the gradient at 2.56, you're going to get a smaller value, until at some point you're going to get a very, very small value that's close to this specific value. So my theta is supposed to approach 0. It keeps on decreasing until it reaches 0, because like I'm going to keep on subtracting smaller and smaller values from that value of theta until it's going to converge. So this game that we're playing is called gradient descent. We're trying to basically descend downwards and try to use our gradient at the point that we're at to decide how we should move, right? So it's called gradient descent because you're gauging where you are, judging where you are, and then using that to dictate your motions, right? So if you are starting off with a guess at theta is equals to 4, if you can find the gradient at that point and take a small step opposite to the gradient. So if the gradient is positive, if you move in the negative direction, that is subtracting the gradient times some small step. This is just a small step. It can be 0.1, right? You can even take smaller and smaller steps. It implies that you're not going to jump like and oscillate like we did if we didn't have a small step, right? Because without a small step, we're going to -4 back to 4, right? So the small step helped us in basically having smaller and smaller steps. In this case, you're going to get like a smaller value. You look at the gradient at that point, you keep on getting closer and closer to this point over here, right? The same can happen on the negative side. If your gradient is -8, remember theta minus the small step times your gradient. Minus and minus is going to give you a plus, so your value is going to get bigger in this direction. So it's going to be -3.5, in this case 3.2, then negative 2.56, and then we're gonna at the end of the day reach 0. So this is what we call gradient descent. We're trying to descend down a structure using, or a shape or a function, using the gradient until we reach the minimum possible point. Okay, I hope this makes sense. I hope I've been able to explain this part a little bit better. So you can basically do very complicated things, right? Let's say that j of theta was something that we knew. Okay, so in linear regression, we introduced j of theta, and we said it's called the cost function. Okay, we introduced something called the cost function in linear regression in the last video. Please do check it out. We introduced something that we call the cost function, which is basically 1/2. I said the half is just for show. Ni is equals to 0, h theta x to the power of I minus y to the power of I. Okay, all of that squared. So we introduced this function, and I said this is a function that tracks the errors that you make, right? It compares the predicted value that you had, and it subtracts that from the value that you know to be true. It tracks that, and it stores basically the error that you're going to make. Okay, so if you want to minimize this, if we want to minimize j of theta, which is basically this function, find values of theta that can minimize j of theta. If you want to find those values, you can see that there's a little squared over here. So we can assume, not necessarily assume, we know that j of theta, if it's, let's say, a squared graph, something like this, we can basically start with any value of theta that we want, any guess value. So we can start here at theta is equals to like 5. If you look for the gradient at that point, okay, if you look for the gradient at that point and we start following that gradient, if it's like this, if the gradient is positive, we move in the opposite direction. So we start with our value of theta, we subtract some small step that we're going to take in the direction opposite, that's negative. In the direction opposite to the gradient, we're going to have smaller and smaller values of theta. So if you use this rule, basically that I've just written over here, we can basically get closer to this minimum possible value, to the point where the errors are 0. What value of theta do we need to get errors that are 0? Okay, so that's very, very important for you to be keeping that in mind. So we can formalize this, right? This looks a little bit informal. We can formalize this and say, whatever value of theta you have, we're going to call it theta j, right? This can be theta 1, theta 2, it doesn't matter. Whatever value of theta that you have should be updated by basically subtracting some small step. The small step, we're going to call it alpha. Okay, in machine learning, the small step is referred to as the learning rate. Okay, the rate at which you learn is detected by the number of steps that you take. The smaller the steps that you take, the smaller basically the more accurate your model reaches this convergence point, right? But it's going to take slower and slower and slower. So if you make alpha very big, you're going to make very big steps that you might overshoot. So that's not going to be good. Okay, and then the gradient, we're going to define it as, in this case, you saw me saying dj over d theta over here, dj over d theta over here, but I'm going to introduce something called the partial derivative. So this is what we call the partial derivative with respect to theta for j of theta. Now, I understand some of you haven't done calculus watching this video, so we're going to explain what this means, right? I think I can make you understand partial derivatives. Okay, so instead of us just saying the gradient, we're going to say the partial derivative with respect to theta. Bearing in mind that instead of just having j of theta is equals to theta squared, we're going to have theta being like, you know, a vector, right? So theta 1, theta 2, theta 3, theta n, something like that. So there are going to be multiple values of theta, and using a partial derivative helps us find the gradient with respect to a specific value of theta that we're concerned with, right? But for now, just keep this in mind. This is what we call gradient descent. Basically, how can you follow the gradient until you arrive at the minimum possible value of theta? Okay. Now, if you Google online for values of j of theta, these graphs are going to show up a lot. These are called basically planes. Like this was a simple case of a 2D where we said you can just follow the gradient until you arrive at the minimum point, right? Let's assume you have like 2 theta values, right? If you have 2 theta values, theta 1 and theta 2, you create a bowl like this plane over here, this structure over here, the more complicated, like if you have theta 4, theta 5, we can't imagine the shape that we create. But it's important to realize that the same principles still apply, right? If you have j of theta now being this complicated function or this complicated representation, what you just do is guess values of theta. Guess a value of theta 1, guess a value of theta 2, and go to that specific point. Okay, let's say the point is here. I'm going to call this point A. And what you do is basically compute the gradient at that point, right? If the gradient is positive, you're going to take a step in the opposite direction. So you're going to update your matrix. You're going to update the value of theta by taking a step opposite, right? And the step size that you take is going to called alpha. Then you calculate the gradient at the point that you're at, and you get a new value which is smaller, which is closer to this point. You do that again. You calculate the gradient where you are. If the gradient is positive, you still subtract to show that you have to move opposite. If you're to increase values of theta, that's bad. You're going to move in the opposite direction. So you're going to subtract, and you keep on decreasing until you're going to reach the lowest value here where you have the least amount of errors. So those are the correct values of theta that you would have guessed. Okay, and then now this mathematical representation can help you find values of theta. So this is what we call gradient descent, right? You start at some point, and you can start here, you can start at some point, and the goal is basically how can you descend downwards until you reach the lowest possible point with the lowest possible gradient, right? Now, if graphs get complicated like this, you can get lost, right? You can either land here, you can land here. So it's very important for there to be like one point, or what we call one global minima, one point that you're gonna basically arrive at. But we're gonna discuss that later on. Okay, so I hope you understand roughly what gradient descent is, right? At least I hope that I can make you understand this, because this is what you call the machine learning gradient descent update rule. Okay, so you're gonna see me in the duration of this course write this as this, right? So this 2 means basically, this 2 semicolon means we're updating values of theta by this rule. Okay, minus alpha, the partial derivative of theta j, j of theta. Okay, so let's start doing some math. We want to find this gradient over here, right? We want to find this expression over here, because once we have this, if you're to plug this in, this can tell you whatever value of theta that you want, right? Now, you might be wondering, well, what's the point of machine learning, right? And I'm going to give you a brief summary so that we can be on the same page, right? The whole point of machine learning is that if it's linear regression, okay, because some of you might be like, oh, I'm lost, I don't understand what we're doing. The whole point is with linear regression, you start off with an assumption, right? The predicted value of theta is going to vary linearly, right? So you're going to have theta 0, x0, plus theta 1, x1, plus theta 2, x2, right? Plus theta n, xn. As values of x increases, the predicted value is going to increase, right? So this is what we call what you expect to get out. This is what we call your prediction, okay? So the whole point of machine learning is to get a computer to guess values of theta. It's a game that we're playing, right? If you can guess values of theta by training your computer based off of known values of y and x, if you're to train your computer to get values of theta, you can basically give it new values of x and can predict something that's true, okay? So we can represent h theta of x, we can represent it as the summation from n I is equals to 0, theta I, x I, we talked about this in the last video, or we can represent this as theta transpose times x, which also talked about this in the last video. Watch it if you don't get it. So this is a representation of the prediction, right? So the prediction can be represented in that specific form, and we said that if you're trying to make a prediction, you're trying to guess and train your model to find values of theta. How can you do that? Well, you can basically you can learn the values of theta, guess what the values of theta are. You can say maybe theta 1 is equals to 2, theta 1 is equals to 5, theta 2 is equals to 3, or something like that. Then you try to compare the prediction that you get out, because you already know x and y, right? You try to guess what prediction you get out, you subtract that, and you get what you call a cost function, which is basically something that tracks the errors that you make. Okay, so this is what you call the cost function. Okay, so you're trying to reduce this, you're trying to minimize this, find values of theta that are going to minimize this. Okay, so if you can find values of theta to make this error 0, basically to make there be no error, that's your correct values of theta that you can plug in here, and your model can guess any out prediction for any given value of x. That's the whole point of linear regression. So we've reached this point where we said that you can start off by guessing any value of theta. So you can start by guessing it, then you can update it by using this rule, right? Subtract alpha times the partial derivative with respect to theta j of theta. And I want to explain what this means if you haven't done calculus. Okay, let's go. What does a partial derivative mean? A partial derivative means with respect to that specific theta value that you're talking about. Okay, so I can give you an example and I can say, let's have a function f of x be equal to x squared y plus xy. Okay, if I were to ask you, can you find the partial derivative of f with respect to x whilst keeping y constant? It basically means differentiate this with respect to x, keeping y constant, so treat y as a constant number. So differentiating x squared y will basically be dropping that 2, so it's 2xy. Differentiating xy, treating y as a constant will basically be like differentiating 2x, which is going to be just y. So this is what we call the partial derivative. It's the derivative of a function with respect to only one specific variable if it contains 2 or more variables. Okay, and then the partial derivative of y for f is going to be equal to, so treat x squared as a constant. So this is the same as 2y. So it's going to be, in this case, the derivative of 2y is going to be 2. So in this case, the derivative of x squared y is going to be x squared. The derivative of xy is going to be x. So this is going to be the partial derivative of f with respect to y, keeping x as a constant. This is going to be the partial derivative of x with respect to y, or keeping y constant. Okay, so this is basically what we call the partial derivative of f with respect to x, keeping y as a constant. So this is what we call partial derivatives, right? You have multiple variables and you're trying to find the partial derivative of something relative to something else. Now, bear in mind that in this case, j of theta is this specific expression. You can expand h theta x to the power of I, right? So the I at the top just means like first training example, second training example. So I can remove it for now and just focus on one example, right? One error that we might make. So simplifying this, j of theta can just be 1/2. I've just removed the summation so that it's a bit simpler to understand. H theta of x minus y. So just focusing on like the first example, the first row as a training example, all of that squared. So h theta of x, if you think about it, is this specific thing. Theta 0, x0, theta 1. Okay, so j of theta can be written as 1/2 theta 0 plus theta 1 x1. Let me put the x. x0 plus theta 2 x2 plus theta n xn. Okay, so that's basically what h theta of x is, and then minus y, all of that squared. So this is basically what j of theta actually is. J, so this theta j that you're seeing here, this j refers to either theta 1, okay? So in this example, it refers to either theta 1 or theta 2 or theta 3 or theta 4, etc. So this is basically what this j represents, right? What theta value are you talking about in this example? So we can see that here I have theta 0, theta 1, theta 2, theta n. So when I say the partial derivative of j of theta with respect to theta j, what do you think that means? It means if I'm looking at theta 1 in this example, if I want to find what theta 1 is, I can start with a guess of theta 1, and then I can update that guess. So this colon means update that guess. So this is what I start with. I can update it to get this new value of theta by subtracting alpha, the partial derivative with respect to theta j. So what this means is basically differentiate this function, right, with respect to theta 1. So find where this theta 1 and
treat everything else as a constant. So theta 1 is the most important thing. So you can see that theta 2 x2 does not have any theta 1, so that's a constant. This is a constant, and the only important thing is going to be theta 1. So this can be theta 2, theta 2, theta 2, right? And you can keep on doing that and keep on doing that. So we want to formalize this, right? We want to basically like create some sort of formal way of doing it so that we don't have to like do it specifically for each given case. So that's why we want to find the partial derivative of k of theta with respect to some unknown theta j, like some general theta j. Okay. I hope this makes sense, guys. So j of theta is basically 1/2 h theta x minus y squared. Remember, I know that h theta of x can be expanded in this form. So basically means this is the partial derivative of this expression, 1/2 h theta of x. So I'm going to drop this theta, right? Just know that this is h theta of x. I'm just going to leave it as h of x minus y, all of that squared. Okay, so this is what we want to find. We want to find the partial derivative of this, right? Okay, so this is the only function that contains theta, right? H of x. Fine. So if I were to give you maybe x minus 1, for example, x minus 1 squared, and I'll ask you to differentiate this with respect to x, what you can do is you can drop the power. So you can drop 2 and have x minus 1, then multiply by the derivative d over dx of whatever is inside this brackets, which is x minus 1. In this case, the derivative of x minus 1 is going to be 1. So it's going to be 1 times 2x minus 1. So this is how we differentiate expressions with indices, right? So make sure you're well solid on that. So in this case, we're going to start, and to differentiate all of this, this is the same thing. Y is a constant. Remember, it doesn't contain any theta. We drop the power. Now you see why there's this half, right? Because by dropping the power, it's going to be 2 times half. I hope you see that. So we're going to have 2 times 1/2. That's so cool. H of x. Okay, let me just put this theta. Where am I kidding? I love putting it. Okay, so h theta of x minus y, all of that squared, right? So you subtract 1 from the power. So subtract 1 from the power, which is going to be 1. So do this to multiply by the partial derivative of h theta of x minus y. Okay, so this is what we call, so let me do this. Partial derivative is like a backward 6 or something like that. Okay, so theta j. Okay, so this is what we call, like differentiation, sorry. So minus y multiplied by the partial derivative of theta j is going to be h theta of x minus y. Okay. Now think about this, right? So I hope this makes sense, guys. I think a lot of people might miss this step, right? You're basically trying to find the derivative of this expression, and I said that you drop the power, subtract 1 from the power, then find the derivative of what's inside, which is what I did, like right here. I hope that makes sense. Okay. If you don't get this, please do refresh your mind a little bit about on differentiation. But if you haven't done calculus, just remember that to differentiate fractions, expressions with like indices, like x, like this squared, you drop the power, you subtract 1 from the power, then you multiply by the derivative of whatever is inside. Okay. So moving on, from this expression here, you know that you're trying to find the partial derivative of h theta of x minus y now. But I already know that h theta of x is basically, so you're trying to find this, is basically theta 0 x 0 plus theta 1 x 1 plus dot 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 theta j x j. Then we continue, minus y, all of that squared. Okay, so like what I'm saying, theta j, like this j, remember, refers to, is it theta 1, is it theta 2? It can be theta 100 that we are differentiating. So you can see that, sorry, there's no squared over here. Okay, you can see that the partial derivative of this means everyone in this expression is a constant, right? This is nothing to do with theta j. This is nothing to do with theta j. The only thing that's left in this example is basically this expression, right, with theta j xj. And remember, theta j is our variable that we're interested in. Xj is going to be a constant, okay? So that means that the partial derivative of this whole expression with respect to theta j is just going to be xj, okay? So what this means is that you're going to have h of theta, x minus y, then you're going to have x of j, and this becomes the partial derivative with respect to some random theta j for j of theta. Okay, this is just specifically for one specific variable. You can do this for like millions of parameters or millions of input features. Okay, but in this example, remember we said that theta of j, the thing that you're going to update in, theta of j, the new updated value will be theta of j, in this case, minus alpha, the partial derivative of j of theta with respect to theta. So theta of j would be equal to theta of j minus the small step that you're going to take opposite to the gradient that you have. And then this is basically h of theta x minus y x of j. And we did this for like one training example, right? We did this for like, like m for like x1, right? We did this for like x1, just x1, right? We can do this for x2, we can do this for x3, so we can generalize this and say whatever value of theta that you have, so we can generalize this and say theta j, whatever value of theta that you have, theta 1 will be equal to, so we can do alpha, the summation, right? And then I is equals to 0. Okay, so I was assuming, sorry, okay, I think this is important to recognize. So I was assuming that I is equals to 0 is like x0 over here, like the 0th training data set. But in some instances, you might not have the 0th training data set, right? So typically, this I is supposed to represent the example that you have, right? So typically, you might have like the first training data set, the second training data set, the third training data set, right? So just for more formality, I'm going to call this I is equal to 1, right? Just to like formally, make it make sense, right? So what this means is that we're just starting with x1, the first training example, then x2, then x3, then x4, then x5, then x6, right? y1, y2. So instead of starting with I equals to 0, this makes it more like mathematically correct and more mathematically nice.
Sorry, I made a mistake here. This is xj. Sorry, I'm saying squared. This should not even be squared. This is supposed to be xj. Then you also put an I to indicate what training example you're using. So x1, x2, and stuff like that. So this is basically the rule that you're going to create. And it's also important for you to distinguish. So there was an n over here. I've made it into an m, right? So it's very important for you to distinguish that we had h theta of x, which was equal to the summation from n I is equals to 0 for theta I, xi. So, right, this was basically theta 1, theta 2, theta 0, x0 plus theta 1, x1 plus theta 2, x2 plus dot dot dot. And you can see that this I was referring to the number of input features. Okay, so like theta 0, theta x0 representing that bias term, and theta 1, x1 representing the next input term. And this m represents the training data set, right? And you can't really start at I is equals to 0. You can and start naming it like I is the first row in a table, I is equals to 0, but it's much better to start at x1, like x to the power of 1, indicating the first training data set. So just for for some housekeeping, the m that you're going to see basically refers to our training example. So whenever I'm talking about that this power I over here, it's going to be running from I is equals to 1 up until m. And then this n is basically going to refer to the number of input features. Okay, and this is basically going to be theta I at the bottom over here, xi, which is just going to run from 0 up until n. Okay, just important for us to make that distinction.
Let's put this in practice. So what this means is that if you want to update the first value of data, which is n is equals to 1 in this case, which is in this case I is equals to 1, right? So for this example, I is equals to 1, you want to update theta 1. What you do is you basically say theta 1. You update it by looking at the previous theta 1. You subtract, and to look at your formula, you subtract alpha, okay? And then you subtract alpha, then you do the summation for m, right? I is equal to 1, h theta x to the power of I minus y to the power of I, all of that squared, okay? So that's basically how you update theta 1. So you look for the summation of all the errors that you can make. That's basically j of theta. Then you do that. So xj, x1 in this example. Okay, so you basically calculate all of this. This is basically the gradient with respect to theta 1. Then you calculate this, you multiply by alpha, you can update values of theta. Okay, so this is what you call gradient descent. Now it's utilized, and your whole goal is basically to try and find the minimum possible value of theta, the minimum error that you can make accurately. Okay. Now, you might be wondering, you might be asking, is this it? Are we done? Well, we're not really. We're left with two concepts that you must understand, and then we'll be done. The first one is batch, gradient descent, and the last one is stochastic gradient descent, and we'll be done. Okay, so if you look at batch gradient descent, bear in mind that we said that theta of j, right, whatever value of theta you want to update, can be updated by following this rule: minus alpha summation for m, I is equals to 1, I is equals to 1 for the whole m being our training data set, h theta x to the power of I minus y to the power of I multiplied by x to the power of I j. Okay, we say that this is what we call basically the gradient descent algorithm, the steps that we take to update and get values of data. Okay, we have what we call batch gradient descent, and what this does is basically it looks at every example, okay. So what it does is it first looks for summation of m, I is equals to 1. So this is what it looks for. So it looks for summation when m is equals to 1 of h theta. Then it does x to the power of I. It finds all of that. And then minus y to the power of I. X j to the power of I. Right. So when j is equals to 1, for example, or when j is equals to any number, it looks through the whole training data set. Okay. So let's say it wants to update theta 1, right, for example. So what it does is it looks through all of this, right? It looks through all of this, then it finds the total error or the total gradient in this example. And then after that, it multiplies by alpha, and then it updates theta 1, okay? Then it goes to theta 2, then it goes to theta 3. Then it recalculates all of this with respect to x2. After it calculates all of that, then it updates, right? So it runs through I is equals to 1. It plugs in what? It runs through the first training example. Then it calculates this thing. Then it goes to x3, x4, x5. It sums that all up, then it updates theta 1. So this is what we call batch gradient descent, right? It calculates the overall error before updating values of data. Now you can see the downside of this. This is very, very expensive, right? It's accurate, I don't want to lie, but it's very, very expensive. It takes very, very slow steps, and it runs through the entire data set. Imagine you have m is equal to 1 million, right? You have to run through 1 million training examples, and you're doing this first for every theta value. Look for 1 million. You look through 1 million training examples. You do it for theta 2, theta 3. You're going to take forever to do this. So that's where stochastic gradient descent comes into the picture. So that's batch gradient descent. That's where stochastic or incremental gradient descent comes into the picture. Okay, what is this all about? Well, with stochastic gradient descent, so I'm gonna represent gradients with contours. So instead of like having this whole pot situation happening here, I'm just gonna represent it with lines, right? Where the most red line represents the lowest point. So I'm gonna represent it like this, then like this. So this represents the lowest possible point. So with stochastic or incremental gradient descent, what it does is that it basically looks at I is equals to 1. So this is what it basically does. So with stochastic gradient descent, it looks for I is equal to 1 to any specific value of n, from I is equal to 1 up until any value of n. And what it does is it runs through and updates every value of theta. Okay, so theta j plus alpha y I minus h theta x I x of j for I for every j. So what this does is it says, hold up, let's go to the first training example, right? So a training example can be, in our example for height, it can be the weight being x1, you have the age, you have parent's height, like all of these being input features. The examples that you have where you have a certain value of weight, certain value of age, certain value of this parent's height, that's what we call a training example. So it looks through the first one and it says, wait, can we update every value of theta? So it updates every value of theta. It's here. Maybe it makes a mistake and it goes here, right? It makes that move. And then it runs for I is equal to 2. It goes to the second training example. Then it updates every value of theta, right? It updates every value of theta. Then it goes here. Okay? Then it does this, it does that, it does that. So it keeps on updating every value of theta every single time until it converges to this specific central point over here. So that's basically how stochastic gradient descent works. You're basically looking at every training example and saying, how can I update all my values all at once for one training example, then update them all at once for the second one? So you can stop it like 1,000. And you might be like, I'm confident enough that this model is accurate, and you shut it down. But for this one, before you even update for Bayes gradient descent, before you even update one value, you have to look through the entire data set and calculate this summation before you even update one value. For the second value of data, you look through the whole data set before you even update it. So sometimes it's going to be ideal to use batch descent, or you can break down into mini batch descent. We're going to talk about that. But that's basically how batch descent and stochastic gradient descent basically differ. In the next video, we're going to introduce the normal equation, which is, instead of basically doing all of this, we can solve an equation, right? We can solve a numerical equation directly for data, right? Bearing in mind that we can use calculus, right? We know that the minimum or the maximum point, the minimum or max point, lies where the derivative of a function is equal to 0. Okay, so if you can find the derivative of this guy and set it to 0, and we basically do cool things, we can arrive at a value of theta specifically without doing any of these gradient descent things. But we are gonna we're gonna stop here. So a brief summary. We started off by introducing what gradient descent is, and we said if we have a random function, j of theta is equal to theta squared, or j of theta is equal to some value function, you can guess a specific value of theta. If you guess a specific value of theta, what you basically do is you look for the gradient at that point, you see what the gradient is, you can basically increase values of theta by following the gradient, but you realize that's a dumb idea. So you move opposite to your gradient and you arrive at smaller values of theta. And we said that if you update this and say theta minus some small step times your gradient moving in the opposite direction due to the minus sign, you can get smaller and smaller values of theta that converges to the minimum point that you want. And we said that we can basically say that's gradient descent, right? So we're trying to use and follow the gradient and descend with it. That's why there's a minus until we arrive at the minimum lowest point that we want. And we say that in linear regression, we introduce j of theta, which is our cost. throughout our entire training data set. I said there's an M, I is equals to 1 for just so that we have some uniformity. So I basically then said that, wait, depending on what your cost function is, you're going to minimize this by finding values of theta. And I said theta is equals to theta minus small step times the gradient. You can formalize this and say theta j is equals to theta j minus alpha. And we said that that small step can be called the learning rate, how fast you learn, basically. And the partial derivative of j of theta replaced just the derivative of j of theta in cases where you have theta being theta 1, theta 2, theta 3, theta 4. And we said the whole point is to start with a guess and then try to find the gradient at that point, and then try to move opposite to that by including the minus. Then you arrive at the lowest possible point. Follow the gradient basically until you arrive at the lowest possible point. And then we introduce how linear regression, the prediction can be represented in this form, and how j of theta can be represented in this form, where this is our whole training example, I is equals to 1. So we say that if our expression is represented like this, we can find this partial derivative. And we did all this math and found out that the partial derivative was very cool, and it was just this simple expression. And we said that we can replace it in this specific manner and put the summation back to show that this is going through all of our training examples. This gives us the updated value of theta. And we said that batch gradient descent is basically a way in which we run through the entire training dataset before we update a single value of theta. But stochastic gradient descent is that for one training example, we update all values of theta, then we move on to the next one. This is good because it's fluctuating a lot, but it will arrive at some point, or sometimes it doesn't, it just oscillates, but it will be close enough and we can shut it down and obtain values of theta. The whole point is to get values of theta so that we can predict h theta of x, the prediction for any given value of an input feature. Thank you.